Dear viewers, welcome to the UGC lecture series in biophysics. This lecture is a general one honoring the Nobel Prize winners in the fields related to X-rays, X-ray crystallography, diffraction and molecular structures. The objectives in this lecture is to detail the Nobel Prizes in the scientific areas mainly related to the crystallography or in that such a determination of molecules. We are going to present a brief outline of the pioneering work by the eminent scientists. In the introduction, we are going to talk about the Nobel Prize and the donor. Nobel Prize is the annual international award to honor the eminent persons in academic, cultural and or social activities. The Swedish inventor Alfred Bernhard Nobel established the prizes in the year 1895 and specified that the bulk of his fortune should be divided into 5 parts for awarding prizes in physics, chemistry, medicine or physiology, literature and peace. Alfred Nobel had at least 350 patents and also was an inventor of dynamite. Synthetic element was named as nobelium to honor him. Let us see what are the few sayings by Alfred Nobel. Success is not a place at which one arrives, but rather the spirit with which one undertakes and continues the journey. If I have 1,000 ideas and only one turns out to be a good, I am satisfied. Contentment is the only real wealth. It is by express with that in awarding the prizes no consideration be given to the nationality of the candidates, but that the most worthy shall receive the prize whether he be Scandinavian or not. So, let us see who are all the Nobel Prize winners related to either X-rays or X-ray diffraction or X-ray crystallography or molecular structure determined by this X-ray crystallography and so on. So, Nobel Prizes have been given for the methods also which have been useful to unravel the molecular structures. As the name X-ray crystallography indicates, without X-rays there is no subject called X-ray crystallography. Without crystals there is no X-ray crystallography. So, coming to the X-rays, W.C. Röntgen received the first Nobel Prize in the field of physics in 1901 for discovering X-rays. What are X-rays? These rays were accidentally discovered by Konrad Röntgen, a German physicist, on 8th November 1895 when he was working with cathode ray tube. As you know, when highly energetic electrons are impinged on a metal target, this energy suddenly stops, some radiations are coming out. So, these are called X-rays. He also contributed to the study of modification of the planes of polarized light by electromagnetic influences of thermal conductivity of crystals and worked out on the influence of pressure on the refractive indices of various fluids. So, these are the other works carried out by Röntgen. So, this is the first picture taken with his bare hand, no, with X-rays. Then in 1912, Max von Laue, again a German physicist, proved that when X-rays fall on a crystal, they produce diffraction. These are just bent, and when you keep a photographic plate and developed, he found black dots. So, in 1914 he was honored for his discovery of diffraction of X-rays by crystal. So, Nobel Prize was given to him. So, Max Theodor Felix von Laue was greatly excited by Einstein's theory of relativity and published papers on the application of his theory. This is additional work he has done. His research was also in other areas like optics, quantum theory, superconductivity and theory of relativity. So, when Nobel Prizes have been awarded, do not think that that is only that field they have been specializing. Yes, they did, but before that and after that also they have been specialized in different fields also. Then if you look into 1915, the physics Nobel Prize, how X-rays are used to determine crystal structure. So, this was given by Henry Bragg and Lawrence Bragg, the father and son, whose pictures are given here. Actually, when Max von Laue discovered that crystals diffract X-rays, he has given 3 equations called Laue equations. When all the Laue equations are satisfied, he mentioned that we have a diffraction effect. But these father and son Braggs, they developed that and they come out with a simple law called Bragg's law. There are 2 planes with a separation d, interplanar spacing d, and when an incident ray is incident with an angle theta, then the diffracted rays will be having a maximum intensity, or diffraction maximum will occur only when 2d sin theta equals n lambda. Whenever the total path difference between 2 rays incident on a parallel plane is integral multiples of wavelength, we have diffraction maximum. So, Nobel Prize was given to these 2 people. This William Henry Bragg's work majorly concerned with the theory of the ionization of gases and ionization curves of radium. He is the inventor of X-ray spectrometer to examine the diffraction of X-rays from crystals. William Lawrence Bragg, son of W. H. Bragg, derived the relationship between the wavelength of X-rays, interplanar spacing, and the angle of diffraction. Nobel Prize was awarded jointly to father and son for their contribution in the field of X-ray diffraction. In 1917, in the field of physics, Dr. C.G. Barkla was given the Nobel Prize for his discovery of the characteristic Röntgen radiation of the elements. In 1909, characteristic X-rays were discovered by Charles Glover Barkla. He was the first to show that secondary emission is of 2 kinds. One is X-ray scattered unchanged, and the fluorescent radiation characteristic to the particular substance. He had shown both the applicability and the limitation of the quantum theory in relation to Röntgen radiation. So, this shows how the 2 radiations are coming out. So, one is your characteristic X-rays, other is the continuous X-rays. In 1929, the Physics Nobel Prize was awarded to de Broglie for his discovery of the wave nature of the electron. This is called a dual nature. These electrons, sometimes they behave like a particle and sometimes behave like a wave. When we talk about wave, we talk about wavelength. When we talk about a particle of, let us say, mass m moving with velocity, we talk about momentum, product of mass and velocity, that is mv. Is there a relation between this wavelength or the momentum, or can the wave nature and particle nature be connected? Yes, he derived a simple relation, lambda equals h over mv, h divided by mv. Prince Louis Victor de Broglie received Nobel Prize for the discovery of wave nature of electron particle. He discovered a series of important findings which form the basis for developing wave mechanics. He also worked on Dirac's electron theory and the general theory of spin particles and the applications of wave mechanics. In 1936, the chemistry Nobel Prize went to P.J.W. Debye for understanding the molecular structure through his investigations on dipole moments and on the diffraction of X-rays and electrons in gases. His major work was on understanding the dipole moments to determine the degree of polarity of covalent bonds and to determine bond angles, and to analyze the effect of temperature on X-ray diffraction patterns of crystalline solids, which is generally termed as Debye. We call it as the Debye-Waller factor. Any organic molecule, in any organic molecule, the atoms do have thermal vibration, and thermal vibration factor is called B, which is called Debye-Waller factor, amounting to 3 to 5 angstrom square. 1937, Physics Nobel Prize went to C.J. Davison and G. Thomson. Here it is for the diffraction again, but diffraction of electrons by crystals. Both crystal is also there, diffraction is also there, but not X-rays. It is diffraction of electrons by crystals. Davison performed experiments on the diffraction of electrons from the surface of a solid crystal. Thomson carried out experiments on the behavior of electrons going through very thin films of metals, which showed that electrons behave as waves in spite of being particles, because this has already been proved by your de Broglie by the equation lambda equal to h by mv. 1946 chemistry Nobel Prize went to Dr. J.B. Sumner for telling that, for his discovery on that enzymes can be crystallized, because those days people never thought that molecules containing thousands of atoms could be crystallized. No? So, just for proving that enzyme could be crystallized, Sumner got the Nobel Prize. So, these are bacterial surface enzymes. He was the first to crystallize an enzyme. Sumner had devised a general crystallization method for enzymes. The 1954 chemistry Nobel Prize was given to Dr. L.C. Pauling, the father of alpha helix. The nature of the chemical bond and its application to the elucidation of the structure of complex substances was thoroughly worked out by Linus Pauling, and application of quantum mechanics to physical and chemical problems, including dielectric constants, X-ray doublets, momentum distribution of electrons in atoms, rotational motion of molecules in crystals, van der Waals forces, are the different fields which have been specialized by L.C. Pauling and have been contributed. Again, second Nobel Prize he received in the field of peace in the year 1962, after seeing the, because in the United States it is compulsory that every person has to serve in the army, and Linus Pauling served in the Second World War. He saw the evil effects of the nuclear bombs on humans. After the war is over, he had a signature campaign in the global level from scientists and banned the use of nuclear weapons on humans. So, he received the Nobel Prize for Peace, two Nobel Prize winners. Coming to the physiology or medicine Nobel Prize in the 1962, it was shared by Crick, Watson and Wilkins for proposing, in fact, double helical structure of deoxyribonucleic acid. Molecular structure of nucleic acids and its significance for information transfer in living material was explained by this structure. The formulation of double helical structure of the DNA with specific pairing of the organic bases, that A, T, G, C we have already seen, opened the most spectacular possibilities for the unraveling of the details of the control and transfer of genetic information. Now, we come to know that they never provided the coordinates of this model, but rather in the next year, when Professor J. N. Ramachandran from the Crystallography and Biophysics Department of University of Madras proposed the triple helical structure of collagen, they objected to it for a simple reason that Ramachandran proposed two types of intermolecular interactions, where they said only one, but finally it is proved that it is 1.5, because sometimes the two atoms can come closer than the sum of the van der Waals radii. Finally, Crick accepted that he should have been given Nobel Prize, but unfortunately Professor Ramachandran was no more. The 1962 chemistry Nobel Prize went to Professors Kendrew and Perutz for solving the structure of globular proteins. So, this is the first proteins for which Nobel Prize was given for solving the structure. Kendrew produced a low resolution 6 angstrom structure of myoglobin in the year 1957 and the high resolution 2 angstrom structure in 1959. Perutz completed a low resolution of 5.5 angstrom map of hemoglobin that the same year and a high resolution 2.8 angstrom map in 1968. Because the resolutions are high, because those days facilities were not available to them, right? No computation facilities, everything they did by manual, even for viewing 3-dimensional view. So, they just have 2-dimensional drawings and piled the 2-dimensional and put a light at the bottom and viewed the structure from the top. So, this difficulty they did, but they had the patience to do the work to achieve. No? So, this is the next prize, 1964 chemistry. A famous lady, Dorothy Hodgkin, she visited India many times and many Indian scientists did their postdoctoral work under her. So, she solved the structures of vitamin B12 and penicillin. Actually, she worked on the structure of insulin also, Dorothy Crowfoot Hodgkin. She received the Nobel Prize for determination by X-ray techniques of the structures of important biochemical substances. She solved many steroids also. She has solved the structures of penicillin and vitamin B12 among others. Her pioneering work helped to unravel the structures of proteins including insulin, which she studied for more than 30 years. The 1972 Chemistry Nobel Prize went to Christian and Finson, Stanford Moore and Stein, because within a fraction, a microsecond you can say, the protein folds. It is the folding which determines the function. If protein does not fold properly, or if protein chain misfold, that causes diseases. So, these three people worked heavily on the folding of protein chains, and Finson proposed that the information determining the tertiary structure of a protein resides in the chemistry of its amino acid sequence and also for his work on ribonuclease. Moore and Stein contribution was the connection between chemical structure and catalytic activity of the active center of the ribonuclease molecule. So, they only started your sequence determine the structure, structure determine the function, of course through the folding. 1976 Chemistry Nobel Prize went to Lipscomb. He was from Boston. So, he just worked on structures of various boranes, and he was awarded this Nobel Prize for his specialization in determining the structure of boranes, illuminating problems of chemical bonding. He has studied the pure electrically neutral boron molecules and also investigated charged boron molecules and other molecules closely related to the boranes. He is a specialist in boron structures. He has also contributed notably in the studies of the structure and mechanism of enzymes. One of the students of Professor G. N. Ramachandran, the founder of Crystallography and Biophysics Department of the University of Madras, namely Dr. Raman, did his postdoc with Lipscomb in Boston. The 1982 Chemistry Nobel Prize went to Dr. Klug for the development of crystallographic electron microscopy and discovery of the structure of biologically important nucleic acid protein complexes. Nucleic acid is very difficult to crystallize, protein also is very difficult to crystallize. When these two are combined, it is very difficult for crystallization. In crystallography, as we have been seeing from the beginning, we should have a single crystal which is growing in length, breadth and thickness. So, in all the 3 dimensional. Suppose you do not have the 3 dimensional structure, then we have plating crystal, then the other alternative is OD electron microscopy. So, Klug has also shown that the 3 dimensional reconstruction of the object can be obtained by collecting the images or pictures in several different directions of projection. So, here I would like to emphasize that this idea was proposed in 1970s itself by Professor G. N. Ramachandran and Lakshmi Narayanan. Unfortunately, in Western science that was not honored. So, here they are honoring. This is already proposed in MRI and those things, it is applicable. How 2 dimensional images can be used to get the 3 dimensional reconstruction. GNR and Lakshmi Narayanan were the first people, okay? He did it in 82, but our people did it in 1970 itself. Then using Klug's method, it is possible to determine the structures at high resolution of functionally important molecular aggregates. So, this is an example of electron diffraction pattern of the crystal of inorganic tantalum oxide. 1985 Chemistry Nobel Prize was shared by a mathematician Herbert Hoffman and a chemist Professor Jerome Karl. I had the good fortune of working with Professor Hoffman 10 months before he won the Nobel Prize and 3 years continuously after his winning of Nobel Prize. I am proud to say that I have 5 publications with Professor Hoffman. This Nobel Prize was jointly awarded to both in the year 1985 for their outstanding achievements in the development of direct methods for the determination of crystal structures. Even though the methods have been developed in 1940s, the methods were honored only in 1985 after the wife of Professor Jerome Karl, namely Isabella Karl, proved that direct methods could solve a dipeptide structure. Then only automation came in the year 1972. The objection is because for the easier mathematics, they assumed certain postulates which were against the laws of physics. They assumed that a crystal with electron density, continuous electron density is replaced by an idealized one consisting of capital N non-vibrating point atoms. So, as per lattice theory, atoms do undergo thermal vibration. So, physicists said you are wrong, and also when they assume all atoms to be point, they said how can you distinguish between an atom containing 8 electron like oxygen or an atom containing 6 electron like carbon. They said is for easier mathematics we will provide atomic coordinates, rough coordinates. You can go to reality by assuming spherical atom and thermal vibration. Even then, just because they do not want the answer to the phase problem being faced in crystallography by physicists, from a mathematician and chemist they openly objected. Finally, they have no other go to accept the formalism given by the people when the dipeptide structure was solved by Carl's wife, and they have been honored. By the time in 1985, more than 40,000 small molecular structures have been determined using direct methods. Direct methods mean directly from measured intensities phase problem could be solved. So, using tangent formula and other things. So, this we are going to have separate lectures during our lecture series. These direct methods are used to directly solve the phase problem by the use of phase relationships called structure invariance and structure semi invariance based on the observed intensities. Herbert Hoffman was the first mathematician even until today to receive the Nobel Prize in the field of chemistry. 1988 Nobel Prize in the field of chemistry went to Disenhofer, Huber and Michel, the trio team, for getting the three-dimensional structure of a photosynthetic reaction center. They explained the function of the thing using the structure determined X-ray crystallography. Hartmut Michel succeeded in crystallizing the membrane bound protein. It is very difficult to crystallize a protein bound with a membrane, and the structure was determined by Disenhofer and Huber, which clearly illustrated the reaction center in a membrane in a photosynthetic bacterium. Dr. Huber has visited India many times and he is a close friend of Professor T.P. Singh, the former professor and head of Biophysics, All India Institute of Medical Sciences, and he visited him many times. 1991 Physics Nobel Prize went to the methods of discovering order in simple systems which can be applied to polymers and liquid crystals. And Jennings received Nobel Prize. He discovered that the methods developed for studying ordered phenomena in simple systems can be generalized to more complex forms of matter, in particular to liquid crystals and polymers. He also developed the fundamental physical theories of liquid crystals which underpin today's understanding of the beautiful and delicate state of matter ubiquitously found today in commercial flat panel liquid crystal displays. In watches you can see these liquid crystals. 1992 Physics Nobel Prize went to Chapok for the discovery of the multi-wire proportional chamber. This is to measure the intensities. He received the Nobel Prize in the year 1992 for his invention and development of particle detectors, in particular the multi-wire proportional chamber. This invention is a breakthrough in technique for exploring the innermost parts of the matter. In practice, even today, every experiment in particle physics uses certain type of track detector that has been developed by Chapok's original invention. 1994 Physics Nobel Prize went to neutron diffraction. So far, we have been seeing X-ray diffraction. Instead of X-rays, they can use neutron. Neutron diffraction can also be used in molecular structure determination if you want to locate hydrogen atoms exactly. So, this prize was shared by Dr. Schull and Brockhaus. Clifford Schull and Bertram Brockhaus equally share the prize for pioneering contributions to the development of neutron scattering techniques for studies of condensed matter. Clifford Schull received the prize for the development of neutron diffraction technique, and Bertram Brockhaus for the development of neutron spectroscopy. The 1996 chemistry prize, Nobel Prize, went to Kerr, Croteau and Smalley for discovering the fullerene form of carbon. it is called C60. 60 carbons are there like a ball, no, that is called fullerene structure. They discovered the new form of the carbon element in which carbon atoms are arranged in a closed shell called fullerenes. Fullerenes are formed when vaporized carbon condenses in an atmosphere of inert gases. They performed the experiment together with graduate students during a period of 11 days in 1985. By fine tuning the experiments, they were able to produce clusters with 60 carbon atoms and clusters with 70 carbon atoms also. 1997 chemistry Nobel Prize went to Dr. Boyer, Walker and Skow for the elucidation of the enzymatic mechanism underlying the synthesis of adenosine triphosphate and ATP, the energy reservoir, and discovery of an ion transporting enzyme. Boyer and Walker shared half prize for their work on how the enzyme ATP synthesis catalyzes the formation of ATP, and Skow received the prize for the discovery of the enzyme sodium potassium stimulated adenosine triphosphate, and it is called ATPase, which maintains the balance of sodium and potassium ions in the living cell. 2003 chemistry prize went to the discoveries concerning channels in cell membranes, and this was awarded to Agri and McKinnon. Peter Agri and Roderick McKinnon shared the prize equally for the discovery of water channels and for structure or mechanistic studies of ion channels respectively. The prize was awarded for the title Discoveries Concerning Channels in Cell Membranes, Structural Biology. They have explored the family of molecular machines which are needed for the cell to function: channels, gates and valves. It is the field of structural biology. 2006 Nobel Prize in the field of chemistry went to R.D. Kornberg for his contribution of molecular basis of eukaryotic transcription. It is a coincidence that his father also won Nobel Prize in the year 1959 in the field of medicine. Roger Kornberg was awarded this Nobel Prize in 2006 in chemistry for his studies of molecular basis of eukaryotic transcription, the process by which genetic information from DNA is copied to RNA. It is a fundamental problem. He also solved the three-dimensional crystal structures of RNA polymerase at atomic resolution, nearly higher than 1.5 angstrom and so on. Now we come to the 2009 Chemistry Nobel Prize awarded to Venkataraman Ramakrishnan, an Indian settled in the US, T. S. Stites and Adayonath, for getting the structure of the ribosome, not only the structure but also explaining the function of the largest molecule, ribosome. They revealed how ribosomes are translating the DNA code to life. DNA is the one, actually ribosome reads the DNA, then prepares the amino acids accordingly and proteins are coming out. So, this shows DNA is read, amino acids are coming out, within fraction we have molecular structures. All the three persons have used X-ray crystallography to determine structures showing exactly where different antibiotics attack the bacterial ribosomes. They still continue working on ribosomes. 2010 Physics Nobel Prize went to material graphene, again connected with carbon structure, to Gim and Novoselov for groundbreaking experiments regarding the two-dimensional material graphene, material which have a lot of strength. They found a way of transferring the ultra thin flakes of graphene from scotch tape to a silicon wafer, the material for microprocessors which are heavily used in electronics. 2011 Nobel Prize in Chemistry went to Shechtman for the discovery of quasicrystals. He discovered icosahedral phase which opened a new field of quasi-periodic crystals. A quasi-periodic crystal or quasicrystal is a structure that is ordered but not periodic. If you look at the crystals we use in X-ray crystallography or single crystal X-ray diffraction, it is periodic, but here structure is ordered but need not be periodic. His work in the area of quasicrystals, ordered crystalline materials lacking repeated structures such as aluminum, gadolinium, manganese alloy was his Nobel Prize winning work. 2012 Chemistry Nobel Prize went to the studies on G protein coupled receptors, and the Nobel Prize winners are Lefkowitz and Kobilka. GPCRs are very difficult to crystallize, and more than for 80% drug discovery problems, these are the target macromolecules. Unless you know the structures, we cannot design the drug molecule. So, Robert Lefkowitz and Kobilka have shared the prize for their groundbreaking discoveries of the structural function of the G protein coupled receptors through which cells sense and respond to the signals. 2013 Chemistry Nobel Prize went for the development of multi-scale models for complex chemical systems, and the three persons who shared this Nobel Prize were Drs. Karplus, Levitt and Warshall. They developed powerful programs to understand and predict the chemical processes. They successfully developed methods that combined quantum and classical mechanics to calculate the chemical reaction using computers, so in silico. So, in summary, what I want to say is that Nobel Prizes that are awarded for the pioneering works of eminent scientists for the scientific achievements directly or indirectly or have used the crystallographic techniques and also methods which are briefly continued in this lecture series. And when we talk about Nobel Prizes, some people they have done noble work, but Nobel Prize missed them, and one such person is Professor G. N. Ramachandran, FRS, the founder of Crystallography and Biophysics Department of University of Madras. All scientists in the global level agree that his discovery of the triple helical structure of collagen should have been given the Nobel Prize, but due to some reason or other it was not given. But luckily the questions made by the referee who objected that model led to an important discovery which is even now known as Ramachandran diagram. People may forget many Nobel laureates, but as long as structural biology exists, Ramachandran cannot be forgotten, because Ramachandran plot is a validated check for the protein deposition in the protein data bank. So, by going through this presentation, you should have a feeling that you should work either in structural biology or you should learn what are all the contributions made by our own people, like Sir C.V. Raman is there, Professor Chandrasekharan is there, GNR is there, many people are there. So, this is only for that I have elaborately presented this lecture. Some of this is related to our biophysics, some of them in general related to crystals, diffraction and other things. So, I thank you very much for your passion in listening. Thank you.